general relativity step by step. We've seen the Kronecker delta before. This is just the identity matrix. Delta ij equals 1 if I equals j, and 0 if I is not equal to j. So it's just the identity matrix. There's a 3 by 3, but it can be any size. What I'm going to do is I'm going to apply the tensor transformation laws, tensor transformation, and see what we get. So what is delta ij bar equal to? In terms of the old original, this is the Kronecker delta in a barred coordinate system, in x bar coords. So what's it equal to? It's going to be a k and l. We've got ij, k, l, di x, di x, di x, di x. Let's get this right. We've got a j on the top there, so that's got to be a j here. That's barred, so that's barred. This L is going to contract with that L there. That's not barred, so that's not barred. That K is going to sum with that K there. What have we got left? We've got an I on the bottom, which must go there, and I think I've forgotten a bar somewhere. There. Okay, so what's this equal to? What's this thing equal to? Delta KL di x bar j by di xl di xk by di x bar I equals what? Oh, well, we only need to consider the terms where k equals l. They're the only non-zero terms. Because if k is not equal to l, if these two terms are different, we're off the diagonals. Where are we? We're on the off diagonal bits, so we're not interested in that. So I'm just going to write k equals l equals, let's say, n, just because I need a new variable and I don't want to privilege k or l. So this thing here, delta kl di x bar j di xl di xk by di x bar I, all I'm doing is copying that, equals sum over n. Didn't really need to say that, but I'm going to say it anyway. Di x bar j by di xn, because I've got l here, but I'm only interested in it when it's equal to n, times di xn, because it's a k there, di x bar I. It's actually easier to recognise if I write it the other way around. If I put di x n by di x bar I, di x bar j n x bar I, all I'm doing is swapping the order of these guys over di xn. We can see that by the total derivative rule that I did in screencast 1, I think it was, that equals di x bar j by di x bar I, which equals 1 if I equals j, and 0 if I is not equal to j. Because if I is not equal to j, by construction, this partial differential is 0. Which is quite an odd thing, which is delta ij. That's quite interesting. Let me go through that whole thing again, because there's quite a lot going on here. What I did, I was applying the tensor transformation law. Well, I was wondering what the Kronecker delta looks like bar j di xl di xk by di x bar I, summed over k and l, equals, and then by calculus and a whole bunch of other things, I showed that that was equal to 1, to 1 if I equals j, and 0 if I is not equal to j. So it must be the Kronecker delta. Well, that's wonderful, isn't it? So what that tells me is that when I transform the Kronecker delta into other coordinate systems, now that's not quite true. When I have the delta and apply the tensor law of transformation to it, as though it's a tensor, it transforms to itself, which is quite peculiar. So that tells me that the Kronecker delta is a tensor. Delta ij is a tensor, and it's a tensor that transforms to itself under coordinate transformation. It's not a physical tensor. It's not something you can go out and measure. It's just a property of, I guess it's a property of space. One thing other before I finish, delta ii equals delta 1 1 plus delta 2 2 plus delta 3 3 plus dot dot dot. Oops. Oh, here it is. Plus delta n equals n. Delta ii equals n, where n equals the dimensionality of the space. It's quite a handy thing to know. I can't quite imagine being trapped in a space and not knowing what dimensionality it's got, but if I was in that situation, I would evaluate delta ii, and whatever it would be, that would be my number of dimensions in my space. So I'm going to stop there.